Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. I'm Taufik Fuadi Abidin, and I'm the moderator for the first plenary session of the 4th International Conference on Electrical Engineering and Informatics 2022, in conjunction with Konferensi Big Data Indonesia 2022. We will have Professor Marcello Bonsangue from Leiden University, the Netherlands, that will talk about information diffusion analysis based on deep representation learning. This is a very interesting topic nowadays. He is joining with us virtually from Bangkok, Thailand. And please let me take a few minutes to introduce our keynote speakers. Professor Marcello Bonsangue, a professor in computer science in the area of system modeling and analysis at the Leiden Institute of Advanced Computer Science, like Leiden University in Amsterdam. He got his PhD in 1996 at the Free University Amsterdam, the Netherlands, and has been a visiting professor for 3 years at Xi'an Jiaotong University in China. It was in 2017 to 2020. He is also a director of education at Leiden University. His research interests lie in the theoretical foundation of computer science, especially on the use of formal method to better understand, model, and trust today's software system. He has been the principal investigator of several national and international projects, winner of international awards, and also co-author of more than 125 international publications and supervisor of 15 PhD students. Well, without further ado, I would like to invite Professor Marcello to deliver his talk in about 25 minutes or to 30 minutes. Professor Marcello, the screen is yours.
Okay, thank you, Taufik. So please let me share the screen first. And should be now visible, right?
Yes.
Okay, so, well, first of all, thank you for all the nice words you said. And thanks also to the organizing committee for inviting me here. And it's a bit pity that I could not be really present at the University of Kuala, but I promise by this that I'm coming. After seeing this video, it's really attractive to be there. And I hope that, we already have some collaboration, and I really hope that our collaboration can go further in all research and education and in general. So, as I already said, Professor Taufik, today I will talk about information diffusion analysis, and in particular on using deep representation learning as a method for this kind of analysis. So let me just say a few words how this interest of mine started. Well, it was during one of my visits in China, in Chengdu, where I met the Professor Fan Zhou, and there we had a discussion while hiking in the mountains in the neighborhood there. We had a discussion on what is a fake news and how one can detect it. I was a bit more old-fashioned, saying that fake news you can detect by just try to understanding what is the meaning of the news, and then try to see if this is real or not. Well, I was saying, yeah, there are different studies now in social science where there are theories which say that you can detect fake news just by looking at the pattern of diffusion that they have in social networks without knowing anything about the content. Well, it seemed to me a bit far-fetched, but well, that was a starting point. And so we hired together a PhD students, Xueqin Chen, and the three of us started working on this topic. So, and that's what I'm going to present to you today. So basically, okay, I will talk a bit about what the information diffusion is in general, and then I will talk about what are the models that we are using, which is a graph neural networks. So while neural networks are more well-known, let's say, well, graph neural networks are a bit less because they have to do with the structured data. So we are not working with just a normal, plain data, but the data that we work on social network, especially, is always represented as a graph, and therefore we need to have a little bit more structure than just having a normal neural network. So I will introduce a bit the model we're using, and then how we really model the information cascade, and then finally arriving to rumor detection. So what is the context? The context is social network analysis, which we all know now. It's nowadays it's impossible not say that no one is involved in social network. They provide enormous amount of information, and there is a freedom of sharing information among all of us. Everyone is can easily share and for free information to basically a very broad audience, and without any problem, and with a reachability of just really worldwide. And typical example are that you have YouTube and Facebook, but there is Line and WhatsApp and so forth. And Twitter is also one of these examples. So these are social networks which connect the worlds, and they make possible this possibility of diffusion of information. And so what is in general, what one want to say, give a definition of what is information diffusion, is basically the study of the spread of the information in a social network from one user to others. Well, this is very general definition, so you need a bit to be more precise on that. But first, why people are interested in information diffusion analysis? So why we want to study this? Well, first of all, yeah, well, we want to study just to see how this information just spread, so that then we can find, for example, what are the elements which makes some information diffusion more successful than others. And second is also because often we want to forecast what are the population, for example, some sharing of information can reach. This is important, for example, when we do some marketing, or when we want to have some prediction of user behavior for social recommendation, but also, and most important, also for the fake news detection. Why is this? Because, yeah, unfortunately, having this democratic way of diffusion of information bring also the possibility of sharing information which is not correct.
Biar mengenal.
Sorry. Okay. So, and that makes possible to share information. Sorry, that is typical example is that during the COVID pandemic, that we see that, for example, there have been a lot of misinformation which has been distributed in social network. Just like, for example, in Europe, there was a lot of ado about the information of Bill Gates implanting via the vaccination of 5G microchips on us. Well, okay. Some people believe in this, some other not. So that was a clear fake news, which really influenced the way of vaccination was in Europe. Why it's interesting also from the technical point of view is because the information diffusion is really depending on the area where the field where this diffusion take place. It can be very different in time and in structure. It's represented as a graph. We already said this, but it can be very differently. For example, if one consider the citation distribution of how the citation spreads from academic world, which takes years, if not decades, and it goes very slowly. The public there is rather limited. If you compare that with, which is the diagram, for example, on the left-hand side of these slides, with if you compare with, for example, the diffusion of information in Twitter, where the thing goes very fast in a couple of hours and then it stops, but it goes very, very fast and reach an enormous amount of people. And this is, for example, graphically represented by the graph, which is on the right. Okay, so what one can do with this analysis? Yeah, would you want to do different things? You want to try to maximize your influence when you to try to know how to do have major influence on your tweet, for example, or just information, just modeling the behavior of a user, or more important also is finding the source of some information, or just you want to model the information cascade and the rumor detection. And I mentioned this last two because this is where I will concentrate in this talk and what our works has been. And why is this? Well, first of all, because we want to try to avoid misinformation, and when we want to predict how the information is spreading. And this has also very nice technical way of description that respect to others that really fit into the deep learning model that we have been using. So what is, well, first we have to give some definitions here to what is an information, how can we model information diffusion? Yeah, we model this by what we call the information cascade graph. This is basically a tree where the user are represented as nodes of the trees, and the edges are just the information, the communication between a user and another user at a certain moment in time. And the time is recorded. So it's not just a simple tree, but it's a tree labeled with times. So where nodes are ordered also by means of some timeline, the timestamps where the information has been communicated. It's a tree and not a graph. It's a tree and not a graph because, yeah, this is more simplicity. We assume that if a graph could be cycle, for example, and that would mean that the information come back to the same user, but the user already knows, so we don't need to have cycle. And could have been done much more compacted in information, but will create more problem in modeling, is if we would have used the directed acyclic graph. But so we use for simplicity the structure of a tree, and the root of the tree is the original message. So where we start and then how this spreads into the network. The cascade graph can be decomposed in two different parts. One is the diffusion graph, which is just a tree, which involves just denote the structure of the evolution of the message from the root message, the source, to all other users. And it can also be decomposed. The second part is what is called the diffusion path. This is just a time sequence where we order the user in a certain sequence of time, and which is forming what is called a multivariate time sequence. And why is this? Because we know how to model with use of the deep learning technique, how to give model for this kind of structures. So then another thing is we have to decide what kind of thing do we want to model. Yeah, there are at least two different levels of modeling. One is the micro level, where we just look only at the local pattern of the social interaction. So that is, we just look only at the single user, and we want to predict, or we want to try to get knowledge on what is the status of the user. So this means that we have to basically know for each user, for example, if would be influenced or not by a single, by every message. Or the opposite is just what is called the macro level, where you do prediction on the full, the information diffusion by just, for example, predicting what is the size of the cascade of the information. How popular, in other words, how popular a certain message will be or not. The second one is simpler because it requires less knowledge, and we will see this in a moment. While the first one is the micro level, it really required to have a full knowledge of the structure that we are talking, and therefore it's a bit more complicated to models. There are models in complex network analysis for doing this kind of things, but I will not talk about this at the moment. So we concentrate at the macro level. And what is the problem basically that we are trying to formulate is the following: that is, we have a cascading graph, the information graph that we have it of the diffusion of the information until a certain moment of time, and then we want to predict how big will be the graph at the other moment of time in the future. So that's that's basically the problem. And this can be organized in two different ways, can be seen as a classification problem. So we want to predict whether the popularity reaches certain thresholds, for example, or can just give a specific number. So this can be seen as a regression problem. And in machine learning terms, so we will just look for the regression problem. So we want to really specify what would be the popularity of a certain diffusion of a message, given the fact that we know some path of the diffusion. And of course, the sooner the better. So the method will be also measured in terms of how fast can the prediction can take place with a certain accuracy. So now if we look what the work which is around, there are several works. There are work which are based really on the content of the message, on the structure, on the temporal feature, on the user feature. So you just define the modeler defines some features, and then we apply machine learning technique for trying to learn this kind of things. That's required that we have to design those features, and so this requires some domain knowledge, which typically we do not have. This typical problem with machine learning. So that's why we would like to extract the feature automatically and use, for example, neural network technique instead of just the machine learning technique. So other methods are just statistical methods based or the methods coming from the complex network analysis community, which just try to, for example, just try to maximize some function of arrival, the intensity function, what is called for arrival of a message at a certain point of time for a certain user. And this is done by using statistical method. But there is all these are based on the hypothesis that we know that the history always influences the future, and this is not always the case for the typical study that we have it here in for fake news, for example. And other methods instead is the using of deep representation learning method. So recurrent neural network or similar, so graph neural network, variation encoding, where you really learn the features by just inserting directly the raw data into the model, and by training the network, and then we will learn that we can do prediction on future networks. So that's just setting the context. So now it's time to just see how what are we going to use it. And we, as I said, we are going to use this graph neural network. So let me just introduce very fastly what they are. So, well, we know what is a recurrent neural network. That is just a neural network where we have some input which is given as a vector in time, so that is repeated in time. And this the neural network is recursively called. So that's why this recurrent. So it's very good for modeling things which have temporal features. And unfortunately, the normal neural network, well, they work with some, a normal recurrent neural network, they work with some update unit, which is just represented by some nonlinear function. And that's where we lose information on the long distance dependencies. So we want to have a little bit of memory. And so there have been introduced methods or update units in recurrent neural network, which includes memories. So for example, there's what is called the long short-term memory unit, where you really have unity inside and you update your memory at every recurrent call in time of your input. And there are other variation of this. There is a simpler variation, which is just what's called the gate recurrent unit, which is very similar in the spirit, at least with the having a memory, adding a memory on your network, so that then you can control better the influence in time or in a time series of the data that you have it. So all of this is necessary because you have structured data, structured in time in this case. But now sometimes the data is not only structured in time, but it's also structured in space. So, and this is the case of graph. So while we have, for example, we use for a simple structured data like images of textual data, we use typically convolutional neural networks. That is, you have your data, which is some Cartesian space, and then you just aggregate information from the data from the neighborhood, so that you just see how the data overlap. Well, in graph, this is not possible because the structure is less structured in a way. So it's a more there is not a precise structure like, for example, this perfect grid of images or of textual information. So why, again, what I said is just why you have it's complicated with to apply the recurrent neural network to graph structures is because how you aggregate information of the neighborhood into a node. In recurrent neural network or in convolutional neural network, this is done by just looking all the neighborhood and shifting your views around the neighborhood. but this cannot be done in a graph because the structure is arbitrary. There is not a number of neighborhood which is fixed a priori. And therefore, the solution is basically to every time compute this kind of convolution by just looking at each node separately. So you just have a specific node, then you look at all your neighborhood node, and you apply a convolution operation on this, so that then you have some overlapping. You can see, you can measure the overlapping information that you have between the node and the node in your neighborhood. And you can repeat this process recursively, so that then you cover your graph structure. The advantage is, again, that we have no sites, specific sites fixed a priori on the number of the neighborhood, and that neighborhood can be had dynamically without any problem. The downsides, of course, is that it's more computational and more intensive. So okay, that's clear. So we have to be careful with that. And it works well when we have structure of data, which is where the features are on the nodes, but not on the edges. And there have been many works around on how to add edge features on the edges, but none of them is really satisfying on this. So there are people in the research community still working on trying to find how to really model graph with the information on the edges, for example. So what we have been using is this type of structure, so the graph neural network, and to apply deep learning methods on with this structure. And the problem with this typical structure is that you have to define a convolution. And to do this, well, we work basically with a lot of linear algebra using adjacency matrices to just represent the edges and the degree of a matrix. And that's, there is a little bit of mathematics involved that help us in how to describe these things. So now we are ready for our model, really, for how to model the information cascade. So when we look at the structure that we have, well, in general, in a social network, we do not have all the network structures. We only have some view of it. And therefore, people just look at only at, for example, some sampling method. So there are two, at least a couple of years ago, there were the two most well-known methods were called the deep cast and deep hoax, and for diffusion analysis. And one was based on random walking around the social network, and the other one on looking at the diffusion path, so just one single path. So that's where we started because basically these two models, they ignore basically all the structure and the dynamic of the system. So we wanted to have a little bit more information on this and try to have a model which comprise both this type of information, which means that we want to have both the structural information represented not as a path, but as a tree, and also the dynamic information which represent the time when this information, for example, the user exchange messages. How do we proceed? So we realize an architecture which is called the CAS-CN, and this is so it's for cascade convolutional network. How does this work? So you have some data, structured data, which is coming, for example, from Twitter, and that represents some cascade graph of the information that is been diffused in the network. And then we sample this graph at fixed amount of time, and we just we keep all the tree structure, not just a sample, or just as a random walk, but mostly as really as a tree. and so that we have both the structural and the temporal information for it. And most importantly, also is the fact that we have a tree. It means that we have directional information. So typically, graph neural network works without direction. So there is a bit of a more technical problem in trying to solve things with direction. So we had to also to solve this kind of problem. How things work? So basically, we have these samples that we generate some sequence of cascade graph from the original one. And then we just, for each of the sequences, we calculated the adjacency matrices for each of these. And then we pass this into the graph convolutional network, which also contain some memories. So that's why it's a deep learning method. For each node, there is a memory. And we also have some fixed decay function for calculating the fact that information in time will be lost. So this way we represent one direction, in one dimension. We have the time information, so this sampling, and another dimension we have the structure, which is the tree structure. So we have we proceed in two different ways. And so it's not just a time series, but it's a time series of trees, if you want to say. And as I said, we combine this with this time decay function, and then this is all put together. Then the rest is just standard. We put all together in some what's called a multi-layer perceptron to just to get all the prediction of the size of the network. So the goal is, given some information that we sample for a certain amount of time until time decay, we want to predict what will be the increase of the size after some amount of time. And so the final output is this number, which represents the increment in time. And this has been compared using two data sets for training the networks. We use the Weibo data set, so it's the equivalent of Twitter, let's say, in China, because there the data was available. And we use also a bibliographic, academic bibliographic database for a citation index. And we compare, so these are two different ways of comparing, both in the structure and time. And the time is very different in the Weibo, because kind of Twitter messages were just very short, so in 1 hour, 2 hours, 3 hours. For the bibliographic distribution or diffusion of the information is really goes much faster. So for 3, 5, 7 years, we look it up. And compared with the other, we see that we have been able to improve the error, the mean square log error, considerably with respect to the most used technique that was at that time. We are in 2029, 2020, which are deep CAS and deep hoax. So having the structural, so the lesson learned is that having structural and temporal information really pay off and improves the techniques, even if add some more computational effort. So therefore we try to improve this, and now we go a little bit faster on this because of time. We try to improve it in different directions. First, we try to not just considering the timestamps by just very, very small and just every single step when every time that the cascade network is improved, but we just we look at the large interval time sampling. And then we also look at the different type of information. That is, we increase the information we had by of the graph by using, for example, not only the direction, but also the high order. That is, we did also what is called a transitive closure of the graph. So we just look at how much the information has influence in the future. And we look at also some other information like the position and the dynamics. And we use a better way of aggregating information using capsule network. And all of this resulted, well, okay, let's just skip this. All this resulted in a new different network model that also learn the decay function not as a standard, as a fixed amount, but learn it dynamically by using just another neural network on top of it. So the architecture is a little bit more complicated because of all those elements, but again, the improvement here is considerably. That is, we really improved with respect to the existing method and even our own method on the cascade network. We improved for at least 10%, as we say. So this is about rumor detection. This was all necessary to start talking about rumor detection. So then, because until now we only studied how much the information is spread and how much this is increased the insights in the future. How can we apply this for detecting the rumor, detecting rumors? Well, first, what is a rumor? A rumor is just a false statement, which is posted in our case in a social network, and then goes from user to user. And the goal is really trying to misleading users. And that's something which creates a bit of a complication, because then how can we say what is a false statement? So typically the way it works is that there are people who read this news and then classify them by just classifying by, for example, rumor, not rumor, or even in a more precise, fine-grained way by just saying if a rumor is a true rumor or a false rumor, something which looks like a rumor but is not, is actually true, or is a really a false rumor, a non-rumor, or an unverified rumor where we don't know what is it. So these are typical classifications that we have it. For simplicity, we just look at the binary classification, rumor, non-rumor, and as I said before, the complexity in trying to understand if something is a fake news is that one has to really go into the content. So one can go into the text-based context, so they really have to have natural language processing technique to understand the text and then check it if it is with some news. Or you may have some, even because of Twitter, for example, you can post a photo and photo can be fake. So you can have also some visual technique to just discover if something is fake, or you can have a combination of the two. So all these are kind of content-based techniques. And some are based really on features that one can assign to text. And some other techniques are really more based on the profile of the user. Other methods that have been actually quite successful is also based on yes. So other users are using credibility base. So you just assign some notion of credibility to user, and some users are more credible than others. So if a news comes from some specific user, then this is considered to be true without knowing, without necessity to read or understand the text. And other possibility just to check if there exists conflict information. So if you have a news and someone else, you find a negation of the news, so there is some conflict, then one of the two must be false. So these are all techniques to discover, but if something is a fake news. But interestingly, some people in social science, so in particular this Bonsangue and his colleague, they did a study on discovering of rumors and non-rumors by just looking only at the diffusion patterns. And they claimed that it was possible to do this in general. Of course, there was a study in social science that was based on only statistical method on some sample of the information that they added. And that was our trigger that said, well, can we create a model such that we can really see if this is true or not? So that was our starting point. So we focus on the retweeting of information and just looking at the diffusion pattern without looking at the content of the news at all. Can we be better than existing method? So that was our question. So we look at the we use what is called this MMRD network, and where we use what is called a train teachers students model. So this is a technique which is used in deep learning for reducing the complexity of the network. So you first train the teachers, and then you use the teachers to pass the information to students, let's say a student network, which so you use the label given by the teacher to train the students, so that you have the students as the facility that is convergent space is already easier to find than the one of the teachers. So the complexity of the network there is easy and get the same solution. So this is a well-known solution in deep learning. So we use this technique and train the teachers, and then we aggregate information with the rest is just the usual way, and we got so we have to finish. So we got the following results, which was actually quite surprising. So without looking at all at the content information, but looking at the pattern of the distribution, we discovered that our architecture was better working than all other existing one using a database on Twitter 15 and Twitter 16, with at least 10% on different way of measuring the usual way. So the results were very promising. We extended this work with the other features, and we just can skip this by using also information on the user. And I can come to the conclusion now, say, well, if you just look at structured data, then the structure is important, not only time. Structure is important, and therefore is the use of a structural network like graph neural network is really important in, for example, the information cascade prediction. And there are techniques for reducing the complexity of this, and this can be used efficiently. And that also we verify that the rumors can be efficiently detected at a very early stage also. I didn't say this, but it can be at a very early stage detected by only looking at the diffusion patterns. So we verify this theory basically in social science to our contest, more technical contest. And of course, if you one adds other extra features, then this could be better to explain the results. So what remains to be done? Well, there is a lot to be done. Well, I think that I leave it for the moment here, and I'm open to questions. So Tofik, I give the floor back to you, so that if there is any question, I'm glad to answer. Thank you.
Thank you so much, Professor Marcello. We have 2 minutes question and answer. I would like to invite the audience. We have one here. Could the committees please share the microphone? I didn't see any question from the chat. Let's hear the first question from the audience over here in Universitas Syekh Kuala, please.
Okay, thank you for the time for Prof. Taufik. Hi, Prof. Marcello.
Hi.
Thank you for the very informative topics regarding to information diffusion. Let me introduce myself. My name is Muhammad Haidir. Currently, I'm pursuing my master's degree program in AI in Universitas Syekh Kuala under supervision of Erasmus Plus DSAI.
Oh.
Well, here I have some questions regarding to the graph neural networks that we have been talked about. What I want to ask is that what are the challenges to build the graph neural network? Well, basically, it's related to my research currently. And the second one is how is the accuracy in general performance? Maybe you can give us a brief description how you obtain it and so on. I think that's all my question. Thank you.
Okay. Yes. Thanks. And that's what. Yeah. This is a very very interesting question and very very good that very good that you are asking them, and you are students from Erasmus Plus makes even more interesting for me. Because yeah, it's a program with Taufik and me and other person are involved directly. Okay, so what are the challenges in graph neural network? First of all, as I already mentioned, one of the major challenges is really how to deal with structured data where the features are on the edges. So where you have information which is per se lives in the edges and not in the nodes. While the structure that I talked here is really having information of the user information is in the nodes, so that's fit very well with the normal framework graph neural network. If you have information on the edges, so that means that you have some dynamical information which is relating two nodes. For example, can be that you have location. The graph can represent the nodes of the places, the location, and then you have streets which move from one to another cities in your graph, represented in your graph as nodes, and then you have information on the node on the edges which represent all kind of restriction that you have on the street, the speed limits, and so forth. Now, this is complicated. There is no at the moment no real good solution for it. You have to translate somehow in the nodes, and you lose somehow information. So that's one of the major challenges. The other challenge is also what I see in these slides that I at the moment see here is what is called a tail node embedding. Is similar challenges that you have in time, where you have also in structure. Some nodes, because the degree of the nodes is very small, suffer from the fact that you have other nodes which have higher degrees. So all attention in the network goes more into the nodes with higher degrees, which so means higher numbers of outgoing or incoming edges, with respect to nodes which are just less important, but we have many of them. So this is what is called a tail node. So people are at the moment try to find embedding of this tail node into some other structure which try to avoid this kind of problem. So because you want to have a fair distribution of the information of the structure and not just giving more weight to the other. So you have somehow you want to work with some kind of weighted graph rather than just a normal graph. So these are the major challenges, I think, in the graph neural network at the moment. You measure, well, I think the other question was about how do you measure accuracy or
how is the accuracy in general, Prof?
Yeah, so in general, they are really impressive. They are really working very well. The price you pay is really in the computational complexity. So they are much lower in the training, unfortunately. So that's why, for example, we use this teacher-student training. So you train, you pay the price of the slower training, and then you model, your model then is more compressed in some other way. So they are computationally more costly, so you have to find technique to reduce this cost. The accuracy is much better than normal networks. So typically, of course, yeah, that's because you just follow the structure of your data.
All right, Professor Marcello. It is also due to time that we have to end this really great first plenary session of ICELTIC 2022. Thank you very much.